All right, welcome back everyone, and buckle up because we have a lot to cover today, talking about how to solve logarithmic and exponential equations. Okay, so we have these two properties that we've written down before, that if I have log base b of b to the y power, that essentially kind of the log base b and b cancel each other out, and we're left with y. Okay, we're going to use that property today. We're also going to use a very similar property, b raised to the log base b, so these bases need to match, of y simplifies to y as well. So kind of these end up canceling each other out, and we're left with y. Okay, so this leads us to two new properties of equality. Remember, properties of equality are things that you can do to both sides of an equation, as long as you do it to everything on both sides. Okay, so one of those is we can take the logarithm of each side of an equation. So let's say we were trying to solve this equation. 5 to some power x plus 1 equals 7. Well, we can take log in any base we want, but in this case it will be helpful to use base 5 so that we can use this property. So that the base of my logarithm matches the base of our exponent here. Log base 5 of 5 to the x plus 1. Well, just like using our property, these will cancel out, and we'll get x plus 1. Okay, but as a property of equality, if you do it to one side, you have to do it to the other. So we do log base 5 of 7. And now we're left with x plus 1 equals log base 5 of 7. Well, this represents a decimal value, something a little bit bigger than 1 that we can find with our calculator, and finish getting x by itself, you'd subtract 1. So it's this decimal minus 1. And this is written as an exact answer, where we didn't have to go to a decimal and convert. Okay, the second thing we can do is we can do something, this is a really weird looking one. It's called exponentiate each side of an equation. So let's say rather than solving this, which would be considered an exponential equation, because my unknown is an exponent, we are now solving what's called a log equation, because my unknown is inside of a logarithm in a couple places. What we can do, because this is log base 2, is we can exponentiate each side using 2 as our base. So that's what this looks like, is we basically write a big 2 here and here, and this expression on each side becomes the exponent on our base of 2. So that's what's happening in this step here. We are exponentiating both sides using 2 as our base. And again, we're using 2 because that's the matching base of our logarithm. And that will give me this property here, where these two will cancel out, and we'll be left with y. So when we do that on both sides, these cancel out, we're left with x plus 1. These cancel out, we're left with 4x minus 3. And now if we finish solving this equation, put your x's on one side, constants on the other, we get 4/3. Okay, now you would normally, of course, have to check this. We'll talk about checking our domain restrictions for log equations in a second. Okay, so that was just explaining the ideas that we can use here. So let's start by talking about solving exponential equations. That's where my unknown's up in an exponent. The first thing we want to do is isolate the base that has our unknown exponent on one side of the equation. So here, 6 has our unknown, right? And we need to isolate it on one side. So for example 1, we'd subtract 5 from both sides. 6 to the 3x minus 1 equals 2. Okay, and now that that's isolated, we can take the log of both sides. That's step 2 here. We want to use the base of the logarithm that matches the base of my unknown exponent. So we want to use base 6 here, not 2. So we're going to take log base 6 of both sides of our equation. Now on the right side, we plug in our 6 to the 3x minus 1. And on the right side, we plug in our 2. So we're taking the log and base 6 of each side. Now, as we said, using our property, log base 6 of 6 to the something, those cancel out. And we get 3x minus 1. Now over here, nothing cancels out. We just get the logarithm, log base 6 of 2. Okay, now remember that this represents some decimal we can get from our calculator. We may need to use change of base formula. But to finish solving for x, I need to add 1 over. And then we're going to need to divide that answer by 3. So log base 6 of 2 plus 1. And then we, of course, divide everything on both sides by 3. So we get this whole expression up top, all divided by 3. So as an exact solution for number 1, we can write that as log base 6 of 2 plus 1 all over 3. Now, if you have a calculator that does log base 6, you can plug this in. You can calculate the decimal version of that if you need to. I think for the majority of our stuff today, you can keep them as these exact exponential forms. But of course, change of base here, you do log of 2 over log of 6 to find that decimal, add 1 to it, and divide your answer by 3. And just to be thorough, if you wanted to know what that answer would look like, so here's the change of base to give me log base 6 of 2. Whoops, actually, I did put that backwards. Apologies. Drop the base, right? Base is in the bottom here. There we go, plus 1 all over 3. So we end up with a decimal value for x that's about 0.462. But we're going to go ahead and leave it as that exact expression for now. Okay, an example like number 2, note that we would not combine these two together. Order of operations, remember I would need to evaluate my exponent here before I multiply. So we cannot combine these and write them as a 6. Instead, I need to isolate this base that has my unknown exponent by, say, subtracting this 3 and then dividing the second 3 away. So let's do that. We'll subtract our 3 times 2 to the x plus 2 equals 18. Divide away our other 3. And now we have 2 to the x plus 2 power equals 6. Okay, so that was all part of step 1. Isolate the base with our unknown exponent. And now we can take the log of each side. Now remember to use the base that has our unknown exponent. So in this case, base 2. So we're going to take log base 2 of both sides of my equation. Remember, it's a property of equality, so you have to do it to both sides. So here we're going to go ahead and plug in 2 to the x plus 2. Here we'll plug in our 6. Now on the left, log base 2 of 2 to our something, that will cancel out. And we'll be left with x plus 2 equals log base 2 of 6. And to finish solving for x, we would just need to subtract 2. And to go to our calculator, if we wanted the decimal version, we would need to figure out what log base 2 of 6 is, that decimal, and then subtract 2 from it. And here is decimal. So if you were calculating the decimal version of that, there's change of base, and then our minus 2 afterwards. Okay, for number 3, same idea. Here we need to get the base of e. This is Euler's number, the base e here by itself. So let's go ahead and get rid of things with addition or subtraction. 2 times e to the x plus 2 equals 4. Divide away our 2. And we're going to have, so those cancel, e to the x plus 2 equals 2. Now if this ended up staying a fraction, that's fine. Just keep it as a fraction as you continue. Now remember here, if my base is e, I want to take log base e of both sides. Well, remember, log base e is the natural log. So we're really going to take the natural log of both sides. That is the same as log base e. So e to the x plus 2. And you can even just kind of write it in there if that helps you remember. But the natural log of e and e will cancel out. Go ahead and put our 2 in over here. So we get x plus 2 equals the natural log of 2. And subtracting 2 to finish getting x by itself, we get x equals the natural log of 2 minus 2. And here is our decimal approximation, which is about negative 1.307. Okay, last one for our exponential equations. This time I cannot write these as powers of the same base or combine them. So instead, to get rid of our 2, if my base is being divided by 2, let's just multiply both sides by 2. And so by multiplying by 2 on both sides, these cancel. we get 10 to the 3x plus 1 equals 6. And now my base is isolated, so we're going to go ahead and take the log of both sides. And when we use base 10, that's actually the common logarithm, which you can just write as log, right? And that does mean our assumed base of 10. So again, if you just wanted to write that in just to prove to yourself those are canceling out, you are welcome to. 3x plus 1 equals, and don't forget to plug your 6 in over here, log of 6. Well, log of 6 you won't need change of base with, so that's nice if you do need to go to a decimal. But let's finish getting x by itself. Subtract 1 over, and then divide everything on both sides. This is going to create one big fraction over here by 3. So x equals log of 6 minus 1, all divided by 3. And there we go. There's a decimal approximation there. Log of 6 minus 1, all divided by 3. All right, for our next section, solving log equations. If we need to, we might need to use our properties of logarithms to condense and get one logarithm on each side. So for instance, in number 5, where we have multiple logarithms over here, we'll need to condense those. Okay, or we have an alternate way of solving them. If I can get one log on each side equals a constant, we can solve that way as well. So I'll do an extra example other than these to talk about that. Step 2 is we will exponentiate each side using the base of our logarithm. And then we will simplify and solve. Okay, keep in mind that logarithms do have a restriction. The inside values have to stay positive. They cannot be 0, they cannot be negative. So if we get an answer and we plug it back in and it makes any expression negative, we got to throw it out, or 0, right? Throw that out as well. So let's try number 3. Use our properties to condense. Nope, we're okay here, but we already have one log on each side. So that's one of our cases here, and that's perfect. So the base of this logarithm on both sides is 2. They match, which is great, because otherwise it's much more complicated. And so we are going to exponentiate each side. So in other words, we're going to use 2 as our base, and we're going to write these as if they are now exponents. So these are exponents on my power of 2. And we're using this property that 2 to the log base 2 of x, those cancel, and we'll get x here, equals, and 2 to the log base 2 of 5, those end up canceling, equals 5. And look at that. We get our answer for x right away. Nice and easy. And this sort of makes sense. Log of something equals log of 5. I mean, those somethings are going to have to be equal, right? X has to equal 5. Now, there is only one place to check plugging this back in, which would be here, and that would be, of course, a positive value. Okay, let's try number 4. Once again, we have one logarithm on each side, so that's perfect. We don't need to condense down, and we don't have to use the log equal a constant approach. This time, though, our base is base 10. It is the common logarithm. So when we exponentiate, we want to use 10 as our base here. So we're now writing this as 10 as our base, and these are our exponents on our base of 10. So here, these will cancel out, and we get 2x squared minus 5 equals, these will cancel out, negative 3x. Now I notice we have a quadratic here. Let's move everything to the left-hand side to solve our quadratic. Whoops, 3x. So we have 2x squared plus 3x minus 5 equals 0. So let's go ahead and see if this is factorable. Okay, and this one does factor. It's 2x plus 5 and x minus 1. You'll get your 2x squared, a negative 2x, and a positive 5x, which will give you the correct middle term. And 5 and negative 1 is negative 5. So this is nice. We set each factor equal to 0. We should get from this factor, when we end up subtracting 5 and dividing by 2, negative 5 halves. And from this factor, we get 1. So we have 2 possible solutions that I would need to check. And I like to look at the simplest one first, because if it makes the simplest looking expression negative or 0, we can throw it out. So for instance, let's even try the simplest number. If I plugged 1 in here, -3 times 1 is -3. And my logarithms cannot be negative. We got to throw out 1. Well, imagine if I plugged this in the same expression. A negative times a negative is positive, so I'm okay with that one. Maybe we need to check over here, though, just to be thorough. If I did -5/2 squared times 2 minus 5, well, this becomes, well, these 2's, sorry, this becomes 25/4 times 2 minus 5. We can reduce these to make this 25/2 or 12.5 minus 5, and yep, that's going to stay positive. So as long as we did all of our other math correctly, only one of them ended up being a domain restriction, and so only x equals -5/2. Okay, in example 5, we've got logarithms on both sides. In this case, let's go ahead and combine these two using our properties. And remember, when there's subtraction, we use the quotient property. And that says we can combine these two as a single logarithm with a fraction inside, in the order of the top minus the bottom. So using the quotient property of logarithms, we can write this as one logarithm on the left. Okay, now we have one logarithm on each side. Our base is e, remember, for the natural log, so we're going to exponentiate each side using e as our base. So these will end up canceling out on both sides, and we're going to get x over x plus 3 equals 6. You might recognize this. This is a rational function. So in fact, even if we put 6 over 1 here, we can find a common denominator, or because it is one fraction over one fraction, you could even cross multiply, which might be easier here. So let's go ahead and cross multiply actually. So let's cross multiply. You can do either diagonal first. 6 here I do need to distribute. 6x plus 18 equals, when you're cross multiplying, x times 1 is x. Well, let's put our x's over here, subtract the x over, and maybe move the 18 to the opposite side. So we get 5x equals -18, and dividing by 5, we get x is -18/5. X is -18/5. Well, let's make sure that everything stays positive. Uh-oh. Look at that guy right there. We're just plugging it in as is, right? It just stays x, and we got a negative value. That's a domain restriction. So we got to throw it out, which means, actually, there's no solution. This is a no solution problem. Okay, our next one. Now, notice I said we can either get one log on each side or one log equals a constant. Okay, here we can manipulate our problem a little bit to get to that one log equals a constant. So let's go ahead and do that. Let's put our logarithms on one side and our constant, this 1, kind of by himself, on the other side. And I think the easiest way to do that is actually to move log base 7 of 8x minus 5 to the other side. Subtract it over. Okay, so now the left-hand side is just 1 equals log base 7 of 24x plus 9 minus log base 7 of 8x minus 5. All right, lots of writing there. Okay, but these are held with subtraction. So once again, we could use the quotient property. Remember, if there was addition, you could use the product property and add their values, right? Or sorry, multiply their values. Here we're going to set it up again as one logarithm with a fraction inside. And it goes in the order of the top divided by or minus the bottom. So 8x minus 5 goes in the bottom, okay, equals 1. So we now have the second form here. 1 log equals a constant. We are still going to exponentiate each side, and we want to use the base of 7. So we're going to write this as 7 to a power, 7 to the first power, which ends up just being 7. Here, these cancel, which is what I wanted to happen, and this equals 24x plus 9 over 8x minus 5. And once again, we have a rational equation we need to solve. And because it's just one fraction equals what we can turn into one fraction, yeah, you could just cross multiply again rather than having to find common denominators. So let's go ahead and just do that. So let's distribute the 7 here. That's just a parenthesis, a poorly drawn one. Sorry, we'll backtrack. Okay, so distributing there, I'm going to get 7 times 8, 56x. 7 times negative 5 is negative 35. Equals, now we're going to distribute our 1, which is pretty easy. That just gives me 24x plus 9. Okay, move your x's on one side of the equation. Maybe subtract the 24x. And since I'm moving my x's to the left, let's move our constants to the right. So let's add the 35 this way. All right, so what do we end up with here so far? 56x minus 24x is 32x. So we continue up here. And then 35 and 9 makes 44. Okay, whoops, sorry, equals 44. Almost forgot my equal sign. There we go. Divide both sides by 32. And yeah, we can go ahead and reduce that fraction. Dividing each by 4, we get 11 eighths. Okay, now remember though, log equations, we have to check that it keeps all logs positive. Well, if I think about it here, positive 24 times my positive number is going to be positive. And then I'm adding 9. It's definitely going to stay positive, so I'm not worried about it being 0 or negative there. This expression I'm a little more worried about, so I'm going to test that one just to be sure. Let's plug in 8 times our answer, 11 eighths x minus 5. So actually these 8s will cross cancel, and I get 11 minus 5, which is 6, and yes, that is positive. Perfect. I think we have our correct solution. And you are welcome to plug it in to make sure that this equation is equal on both sides, but to save ourselves some time, we're running a little long, we'll leave it there. Okay, definitely do more examples of this in class. Hopefully exponentiating both sides sort of makes sense, and what value to use for that, and taking the log of both sides makes sense. So we'll definitely be using those two things anytime we need to solve an exponential or log equation.